Hello again. Do you know how to define the term reaction rate? And do you know why reactions all occur at different rates? Amira will tell us more.
Let's take a look at another experiment. I have a concentrated acid solution in this test tube, and I'm adding strips of aluminium. There are bubbles forming, so there must be a chemical reaction taking place. Chemical reactions only occur when molecules collide with each other to form new molecules. These collisions are called effective collisions. For effective collisions to take place, particles need to have just enough energy, and they need to collide at just the right angle. For some reactions, the products form quickly, while in other reactions, it may take a long time. We say that the rate of reaction is different for these reactions. We define the term rate of reaction as the amount of product formed per unit of time. The rate of reaction is dependent on the number of effective collisions taking place. When a large number of effective collisions occur in a specific time, more products form and the rate of reaction is high. But when the number of effective collisions in a given time is small, fewer product molecules form, and we say the rate of reaction is low. When we have a certain number of reactant molecules, the fixed number of product molecules will form too. We can never change the amount of product formed. We call the amount of product the yield of a reaction. However, we can change the time it takes for the product to form by changing the conditions that affect the rate of reaction. Remember, the 5 conditions which affect the reaction rate are the surface area of solids, the temperature, the concentration of reactants, pressure in gases, adding a catalyst.
So we know that the amount of product formed in a certain time tells us about the rate of reaction, and that reactions can occur only when there are effective collisions. Amira also showed us that the yield of a reaction is always the same because it is based on the amount of reactants, but the time it takes to form the product can be changed in one of 5 ways. These 5 conditions are surface area, temperature, concentration, pressure, and the use of a catalyst. It's all very well talking about the reaction rate, but we still need to actually measure whether a reaction is fast or slow. Amira will tell us some practical ways to find the rate of reaction of different reactions. Amira has some examples for us, and she gives Kani and Rahim an investigation too.
One way of finding the rate of a reaction is to measure the amount of products formed in a certain time. We can measure the amount of product by finding mass, number of moles, concentration, or number of particles. If we were measuring the number of particles of a product, for example, we would take measurements over small time intervals, tabulate the data collected, and then plot a graph. Let's consider the combustion of magnesium in oxygen as an example. Magnesium reacts with oxygen to form magnesium oxide. Before the reaction starts, we have magnesium atoms and oxygen molecules as the reactants. There is no product or magnesium oxide. The reaction starts when energy is added, and then the atoms of magnesium and oxygen molecules combine to form magnesium oxide particles in a very short time. Can you sketch a graph to show how the number of product particles changes for this reaction? Notice, at the start, there are no particles of magnesium oxide. But once the reaction starts, the number of product particles increases rapidly and then remains constant. We can use the gradient of this type of graph to find the reaction rate. Remember, to work out the gradient of a straight line, we use the formula change in y divided by change in x. We can use the same formula for a curve to find the average gradient between 2 points in time. Notice, in the first time interval, the average gradient is very steep and positive because a large number of product particles formed in a short time. We can say that the reaction rate is high. Notice, in the second time interval, the gradient has decreased, and we say the reaction rate has decreased too. In the third time interval, the gradient is 0. There is no more change in the number of product particles because the reaction has stopped. The rate of reaction is 0. We used a graph that plotted the number of product particles against time. We could also have used mass of products, moles of products, or concentration of products. We can use any of these graphs to calculate the reaction rate, or we can use the following formula. Reaction rate equals the change in the concentration of a product over time. We use square brackets to indicate concentration. Remember, the number of product particles formed is linked to the number of particles of reactant we have at the start. Can you predict what happens to the number of particles of reactants during the reaction of magnesium and oxygen? It will be clearer if we represent the changes in the number of reactant particles on a graph. At the start, the number of reactant particles is initially high, but in a very short time, the number of particles of reactants decreases. Eventually, all the magnesium atoms and oxygen molecules have reacted, as shown by the steep curve on the graph. Notice that the gradient of the curve is negative because the reactants are being used up. The gradient is large to begin with, but becomes less steep until all the reactants are used up. So we can define a second formula of reaction rate as the reaction rate equals the negative change in the concentration of a reactant over time. Now let's put this theory into practice. Kanye and Rahim are working together on an investigation about reaction rates. Let's see how they are doing.
So, what's the investigative question?
How does the temperature affect the reaction rate?
And how do we investigate this?
Hi guys, do you need any help with what you're doing?
Well, we're investigating the effect that temperature has on the reaction rate, and we're not really sure how to do it, so we need your help.
Okay, you will need to decide on a reaction that you can test. What about the reaction we did in class? Sodium thiosulfate reacts with hydrochloric acid to form a yellow precipitate of sulfur.
Oh, I remember that one. It's where the solution turns into a milky yellow color.
Yes. Can you remember why it goes milky and not clear?
I think it's because of the sulfur.
Yes, that's right. The sulfur couldn't dissolve to make a solution, so it formed a solid precipitate. we can measure the time it takes for a certain amount of sulfur molecules to form.
That will be a good reaction to investigate.
Right. We need 3 small conical flasks, a measuring cylinder, 3 pieces of paper with a black cross drawn on each one, dilute hydrochloric acid, sodium thiosulfate solution, ice water and hot water, and 1 stopwatch. Right. You now have your investigative question and your apparatus. What do you think your hypothesis will be?
Well, I think the hot reaction will react the fastest.
Me too. I think the warmer the reactants, the faster the reaction rate. Is that correct?
That's right. Your hypothesis is your answer to your investigative question. And now we need to test your hypothesis. Kanye, pour the solution of sodium thiosulfate into each flask.
So how much must I pour?
30 cubic centimeters should be enough. How do you think we can make it a fair test?
By making sure we have the same amount in each flask.
Yes, very good.
So all 3 flasks have the same amount of sodium thiosulfate solution. So what's the next step?
Well, what are we testing again?
Well, we're testing the effect that temperature has on the reaction rate.
Right. So what do we need to change?
I think we'd need to change the temperature.
Right. Rahim, place 1 conical flask into ice water, 1 into hot water, and leave 1 at room temperature. And now we have sodium thiosulfate solutions at 3 different temperatures. We need to place each flask on a piece of paper with a black cross on it. How do you think we will tell which reaction rate is the fastest?
Well, we know that the reaction causes a milky solution, so the one to turn milky first will show the fastest reaction.
Yeah, when looking through the solutions now, we can clearly see the black crosses. But if we keep on watching them, the cross that disappears first, that one will have the fastest reaction rate.
Right. Now pour 10 cubic centimeters of hydrochloric acid into a beaker, and then start the stopwatch. Remember to stop the stopwatch when the black cross disappears in your flask. Right. What did you notice?
That the black cross underneath the hot conical flask disappeared first, then the one at room temperature.
And the time proves this as well.
Yes, you have quantitative and qualitative results.
We've got what?
Let me explain. Qualitative and quantitative. Think of qualitative as a quality check. We can see any changes or differences. These are our observations. And think of quantitative as quantity values. We can measure the changes or differences. Do you know how we can make the results of the experiment more accurate?
Maybe if we get more readings.
Yes, that's right. By repeating experiments, we get more accurate results that we can trust.
That's great. Now we can finish the investigation.
Oh yes, we have our results now, but we didn't write our dependent and independent variables.
I don't know what they are.
Well, what part of the investigation did we change?
We changed the temperatures.
Right. And because of that change, what part of the investigation did it affect?
It affected the rate of the reaction.
Yes. So because of the change in temperature, the reaction rates changed. Did the temperature depend on the reaction rate, or did the reaction rate depend on the temperature?
I think that the reaction rate depended on the temperature.
Good. So which one was the independent variable?
The independent variable was the temperature because we controlled it. The temperature wasn't affected by anything else.
That means that the reaction rate is the dependent variable because it changed due to the different temperatures. Now we need a conclusion. We have the result, but it's more complicated to write the conclusion.
The conclusion should agree or disagree with your hypothesis in the beginning.
So our hypothesis was, the warmer the reactants, the faster the reaction rate.
And your results confirm your hypothesis.
That means our hypothesis was correct. The warmer the reactants, the faster the reaction rate.
Well done, you two. I'll leave you now to write up the method. We have just shown one of the ways to measure reaction rates. In reactions where a precipitate is formed, we can measure the reaction rate by determining the turbidity. Turbidity means measuring the amount of solid product formed over time. We can also use a change in color to measure reaction rates. Sometimes a reaction can result in a change in color from reactants to products. The faster the color changes, the faster the reaction. Let's look at the iodine clock experiment to see how the color change shows the rate of the reaction. The reaction happens faster with more concentrated solutions. Do you know how we could measure the reaction rate of a reaction that produces a gas? I hope you thought of this next idea. We could collect the gas produced. How do we collect a gas? One method is to use a gas syringe. Look at this. Here we have magnesium reacting with hydrochloric acid. Hydrogen gas is produced. As the gas forms, it rises and pushes the plunger of the gas syringe back. We can then measure the volume of gas produced in a specific time. There is another method we can use to collect a gas to measure it. That is by the downward displacement of water. You see, we can collect the carbon dioxide when a carbonate reacts with an acid. We fill a measuring cylinder with water and carefully turn it upside down. Then we place a delivery tube from the flask to the mouth of the measuring cylinder. We can now catch the bubbles of carbon dioxide. The carbon dioxide pushes the water down. We can then measure the volume of gas produced in a certain time. We have just seen some methods of collecting a gas to measure the amount of gas produced by a reaction. We can also measure how much of the reaction mixture is left behind when a gas is released. Can you think of a way to measure the reaction mixture? If we let the gas escape from an open container, the reaction mixture will decrease in mass. We can then work out the reaction rate by working out the change in mass in a set time.
Amira gave us a lot to think about. Let's recap. We saw that a practical way to measure the reaction rate is to measure the amount of product formed in a given time. We could do this by measuring the mass of the product, the number of moles, the concentration, or the number of particles of the product. We also learned that it is possible to draw the change in the amount of product on a graph and then use the gradient of this type of graph to find the reaction rate. Kanye and Rahim also showed us that it is possible to test for the effect of things like temperature on reaction rate, while Amira used the iodine clock to show how concentration of reactants affects reaction rate. Kanye and Rahim used the quantitative method to measure the rate of the reaction, and the iodine clock reaction was a qualitative method using observation. Amira also showed several other quantitative or measuring methods, using volume in a reaction that produces a gas and mass of the reactant. To get to grips with all of this, I suggest you try some of the questions in the rate of reaction task video. Also look on our website www.mindset.co.za/learn for more details on this series. That's all for now. See you next time. Goodbye.